Another question here. We have a simple electrostatic precipitator. I don't know what that is, but if we read further we will probably learn something. It's used to collect ash and dust in a factory chimney. It can be made from two parallel metal plates mounted vertically as shown in the diagram. The diagram is missing, so I'm going to redraw the diagram for the questions that it relates to. 40,000 volt power supply charges up the plates so that a strong electric field is maintained between them. The separation of the plates is 0.78 meters. Now, really important, let's highlight the important details. We'll just circle them in this case. So 40,000 volts between the plates, that is the separation of the plates, and from that we know with the formula E equals, E being the electric field strength, is voltage divided by the distance between the plates. We can calculate the electric field anyway. That's what we're getting at. So A actually asks us to calculate the strength of the electric field at point X. Now, we can't see where point X is. I'm going to make it up shortly so that we've got some context for the rest of the questions, but we know that the electric field between two parallel plates is going to be uniform. So it actually doesn't matter where inside or between the two plates the point X is, because it's a uniform field. So we can calculate. If it was a point charge, that's when you have problems, because the field further away from a point charge will decrease according to the inverse square law, the same as gravity does. So the further your radial distance from the centre of the Earth becomes, the greater is the drop-off. In fact, it's an inverse square relationship as well. But anyway, we can look at that another time. So anyway, calculate the strength of the electric field at point X, which is at the centre between the plates. We're actually told where it is. But anyway, here's the plates. It's at the centre between the plates. Electric field strength is voltage divided by distance. We've got 40,000 volts divided by a separation of 0.78 meters. We're going to assume both of these are to 2SF for the sake of our final answer. We're just going to plug that in and calculate it. To two significant figures is 51,000. Let's put a little comma there as a good practice to help put the separation in our mind and keep an idea of the magnitude of that. You can use decimal places where other places where they're required, but some people I've noticed use commas as a convention in their country. Just be aware of that. But even better is just to leave a little space between you group your numbers in threes, so that it's. Anyway, we're missing one thing off here, that's the units. We could have put newtons per coulomb, but in this case we've calculated voltage divided by distance, so let's call it volts per metre. There we go. Question B says, what is the electric field strength at point Y? Now, if that's point X in the middle there, anywhere within this field, if Y occurs within that, it's going to be the same. So we don't have the diagram to know, but we're going to call it the same as X, which seems reasonable. It's testing whether you understand that it's a uniform field or not. So the field is constant. That means it's providing a constant force at any point within those plates. The only time you would get a change in that is if it was outside the plates, in which case there would be a difference. You wouldn't know what it is, or right on the edge here where the field starts to bend, then it's going to be a little bit different as well. But everywhere inside the plates is fine, is constant, is uniform. But if it's outside, like in that point, or at the bending part, you've got no way of calculating what it will be, not at this level anyway. So I think this was a trick question. I haven't got the little diagram, and it makes sense anyway that it should be the same as at point X. The real question, C, is our tricky bit. We've got a single piece of ash, has a charge equivalent to 1 electron. Let's just write that down. E, negative 1.6 times 10 to the minus 19 coulombs, so we can remember that for later. A charge equivalent to 1 electron as it enters from below the plates. This is exactly 0.30 meters from the positive plate, which, if we're remembering electrons, negative charge, it's going to be attracted to the positive plate. So it says calculate the change in electric potential energy of the electron just before it hits the positive plate. So what we're assuming here is that the distance that is travelling is 0.30 meters. Let's just shift that across there. And we've got the charge and the electron there. So we can work out the voltage gained, the energy gained. Okay, getting myself a wee bit tangled and tongue-tied. So just restating, we're working out the energy gained, because it says the change in potential energy of the electron just before it's a positive plate. So the energy gained without a wiggly line under it by the electron as it covers that distance. Remember, the energy gained is equal to the work done on the charge, on the electron thingy that's charged. And remember, work is always force times by the distance that it's moved through. So in this case, we have a force of well, let's look at our equation. I'll write it down here as part of this. Electric field strength equals force per charge. Okay, we want to know the force on it, which is going to be the electric field strength. Remember, electric field strength has got the wiggly line under it. Electric field strength times by the charge. In this case, the charge will be the charge on electron E. So we can work out what force is applied, which is going through here, and the distance that it moves through to work out the total energy. Just restating exactly what we're doing. So let's go ahead and do that. Remember, 51,000 times by 1.6, in fact times by negative 1.6, but we don't need to worry about the negative for our calculation here because we already know the direction it's going. 1.6 times 10 to the minus 19 coulombs. And if we wanted to times it by distance as well to get the work, we would just multiply that by distance on the end. So in fact, let's write that out completely because it's going to save us just a fraction, a bit of time if we would do this in an entire process. The energy is equal to the work, which is equal to the force times the distance, which is equal to the electric field strength times by the charge on an electron, because that's the force, that electron, E times E with a wiggly line over it times E, is the force times by the distance that it moves through. Now, let me just write this equation in such a way, if you are not careful, you'll get yourself really mixed up. This is E equals E times D. Okay? 3 different E's in this equation. Let's just rapidly highlight what they are because it's so important to get this right. This first E is the energy that is gained. The second E, with the wiggly line under it to distinguish it from the first E, so the second E is the electric field strength. This third E is the electron charge, a special constant, so it's given a special letter, small e by itself. And then we've got D, which is the distance it moves through. So let's plug all of those numbers in to try and find what E here actually is, the energy gained by. So 51,000 times by 1.6, in fact it's negative, but we don't need the negative because we know the direction, times 10 to the minus 19, times by 0.30 meters, 30 centimeters it moves through. Let's just double check that. Yes, 30 centimeters it moves through. And then we plug that into our calculator and find our answer equals 24,615 times 10 to the minus 19. So I've just multiplied the 51, that actually looks like a 3, so you've got to be careful when you're writing things down. 51,000, in fact I've used the unrounded value of that from the previous calculation, which was, I can't remember, 51,000 something. So 51,000 times 1.6 times 0.3, and then that gives us 24,615 times 10 to the minus 19. We can actually reduce this further because we've got, this could be written as 2.4615 times by 10 instead of the minus 19. We've shifted that decimal place 1, 2, 3, 4 places. which means we take 4 off there, minus 15. And the units for this is energy gained, so we don't need to worry about electric field strength, electron charge and distance. Energy gained is joules. Nice and easy. And the final answer, we should round to 2 significant figures as per the data given to us in the question. So 2.5, because 6 is greater than 5, so it rounds up for that next figure. 2.5 times 10 to the minus 15 joules. That is the energy gained by that single electron charged ash piece as it moves 30 centimeters.